Hey everyone, this is Darshan Santa. In this video, we shall be talking about how to evaluate limits analytically. So let's get started. So let's just go ahead and begin with a little warm-up. So I've given you a graph and a function, and I want you to evaluate the limit as x approaches 0 of that function there using the graph. So take a minute if you want to and pause the video and go ahead and try to solve that. Okay, let's go ahead and try it now. Let's go ahead and go over it together. So notice that as your x values slowly get closer and closer to 0, your y values and this graph are slowly getting closer and closer to 0 as well. They're starting to get closer and closer to the x-axis. Okay, so from the left, this would just simply be 0. Okay, now what about from the right? So notice that as you take values that are very closer and closer to 0 from the right, as they get smaller and smaller, the graph also is slowly starting to get really, really close to the x-axis. It's getting really, really close to 0. So therefore, we can infer that the limit as x approaches 0 from the right of g of x is also equal to 0. So since these two are equal, we can say that this is just simply 0. Woohoo! That's it. Now let's look at part 2. Sorry about this stuff, but you're basically being asked to evaluate g of 0 using the function, and g of 0 is basically this. So g of 0 is when you plug in 0 in place of x, so that would be 4 times 0, which is essentially 0. Now I want you to make one observation. Notice that the two are equal, or rather it should be this. Notice that the limit as x approaches 0 of g of x is the same thing as g of 0. So as you can see, we can find the limits of functions by simply plugging in the given x value. So you can essentially, if you want to find a limit at some point, you can plug in that value and you'll get the point. And intuitively speaking, this does make sense, because as you get closer, as you plug in values that get really close to some x value, as you plug in x values really, really close to some other x value, then your y values, or your f of whatever, is constantly going to get closer and closer to as if you had actually plugged in that x value. So for example, if you plug in values really, really close to 0 in this function right here, you're eventually going to get really, really close to what you'd actually plug in if you plugged in, what you'd get if you just plugged in 0. That's the concept behind this. I hope you understood that. So that's essential to evaluating limits analytically, so make sure you get that. If you have, then let's go on. So finding limits analytically. This is the process of evaluating a limit, it's a typo, through algebra. So this is just a review of what we went over, the definition. Well, it is mostly just plugging in the x value. There are other situations that could arise. For example, the limit as x approaches 1 of 1 over x minus 1. If you plugged in 1, you would get 1 over 1 minus 1 equals, you get 0. 1 over 0. And you can't divide by 0. At least we don't know how to as of now, because we don't have a definition for what happens if you divide by 0. It's undefined. So therefore, you can't do this right away. So in this video, we're going to go over some techniques of how you would evaluate limits if you had such situations like this one, for example. Okay. All right. So here are some possible remedies that you could resort to in case you couldn't see a way you could just plug in directly. So you could factor out. This is one you're going to see more often. And this is basically whenever you have polynomials. You should always be looking to factor out. Multiplying by a conjugate is basically when you have a radical, like square root of x, whatever, common denominator. This has to do with fractions. Okay, or expand. This is when you have stuff like square. If you have stuff like that, then you can go ahead and expand it. Sometimes it helps. So if any of these work, you have what is called a removable discontinuity, or a hole. In other words, your graph would be like this, but then you have just a little hole at that one point where you're finding the limit, and then you keep going on. So it's undefined just at that one point, and that's the reason you can't plug in directly. So here's the essential idea here. All these methods, all these remedies, they make the function, they make your function prettier. That's important to realize. They just make it prettier. They don't actually change the function itself. They just make it prettier so that you can plug in and then actually evaluate the limit that way. That's all they do, okay? So if they don't, then you have what's called an essential discontinuity. And that we will cover in another video because I don't want to spend too much time on that right now, okay? Let's go. So here are some examples for us to do. So the limit as x approaches 0 of 2x minus 3. So the first thing you should do is just ask yourself, can you plug it in? So the first question you should ask yourself, can you plug it in? Can plug in. Can plug in. And in this case, yes, because it's a linear function, I can plug it in without violating any rules of math. So this would just be 2 times 0 minus 3, which is negative 3. Okay. Now, what about this thing? Can I plug in, let's go in order. So what about this thing? Can I plug in 4 right away? Well, no, because I'd get something over 0 because I have x minus 4 in the denominator. So then I have to take my second step, which is use a remedy. One of the things we talked about in the previous slide. So in this case, I see a quadratic up here. So whenever I see a quadratic, I think polynomials, factor. So I'm going to go ahead and try factoring that just to see what happens. And if it doesn't work, then you'll just know it doesn't work. So you have an essential discontinuity. So right over here, we see that if we pick two numbers that add to equal 8, negative 8, and multiply to equal positive 16, those would be negative 4 and negative 4. So x minus 4 times x minus 4 over x minus 4. And this is technically the limit as x approaches 4 of. See, I haven't actually taken my limit yet. I've just manipulated this function to look different. And now I can go ahead and cross out one of these x minus 4s, and I'm left with this. The limit as x approaches 4, sorry, my writing's a little bit unneat, of x minus 4. Now I can go ahead and plug in my 4 and there's no problems at all. That's basically 4 minus 4 equals 0. Voila. So the answer to this is simply 0. Now let's try one last example. So as you can see here, I have a radical in my denominator here, and that's kind of bothering me. But the thing that's really bothering me is that I can't substitute in 3 here because that would equal 0, and the square root of 0 is 0, and you can't divide by 0. So what should we start with? Well, the first thing we should probably start with is we should probably try to factor this to see if we can cancel anything out. So let's go ahead and write that out. The limit as x approaches 3 of what two numbers add to equal negative 1 but multiply to equal negative 6. That would be negative 3 and positive 2. So that would be x minus 3, x plus 2 over square root of x minus 3. Now at this very moment, I'm kind of stuck because I don't know what to do. So what I can do is I can go ahead and rationalize. Because I have a square root, I'm just going to think rationalize and just see where that goes, because if it doesn't work, then I can just try something else. So I'm going to multiply by the square root of x minus 3 over the square root of x minus 3. And notice that this is just multiplying by 1, because this in In essence, this is just equal to 1, but I'm just multiplying by 1 in a way that makes my function look different. So because I'm not changing its value, I just want to make it look different for my purposes, okay? So let's go ahead and evaluate what that is. This would be the limit. Again, notice I'm carrying my limit to each operation. I haven't taken the limit yet, so I need to be careful that I don't misrepresent what I'm doing. This is x minus 3 times x plus 2 times the square root of x minus 3. And these two multiply, and you get just x minus 3. Now, is there anything I can cancel out? Well, there sure is. I can cancel out the x minus 3's, and I'm left with the following. The limit, as x approaches 3, of x plus 2 times the square root of x minus 3. Oopsie daisies. Okay, so that's what I'm left with. X minus 3, that is. I'm not sure if you can see that. But yeah, now I just go ahead and plug in my 3, and I get 3 plus 2 times the square root of 3 minus 3. And since this multiplies to equal 0, you get 0. And since anything you multiply by 0 is just 0, the answer is just going to be 0. Okay, there's our answers. So just one final reminder before we end this video. Even though f of x is undefined at certain values, the limit still exists since we do not consider what happens at the exact value when evaluating limits. And as you can see, both of these examples, we couldn't find what f of 3 was, or g of 3, whatever. But we could find the limit because we only consider values that get that this thing gets really close to as it gets to 4. Like if it said find the function of 4, then we would just say that's undefined. But because we're finding the limit, we can just say that we're finding values that are close to it. That we can just say we're finding what it approaches. Okay, so I hope that helped. That's the end of this video. Thank you for watching, and please do subscribe. Tell me how I'm doing. I really want to make these videos the best content possible. So thank you. Have a nice day.